The standard free energy of formation, so that's just when we add that little small f at the very end, is the free energy change associated with the formation of a substance from its component elements in their standard states. So we can actually calculate a delta G reaction the same way we've done delta H's and delta S's. So if I was to give you a bunch of delta G values for specifics, then we could actually calculate our delta G from those values. So it's the same exact process, we're just plugging in the values from a chart. Here's an example, calculate the delta G of reaction for the combustion of propane. If I was to look at the chart in the back of the book, I would be able to find that the Gibbs free energy for CO2 is negative 394.4 kilojoules per mole. The Gibbs free energy for H2O is negative 237.1 kilojoules per mole. For propane, negative 23.4 kilojoules per mole. And the Gibbs free energy for O2 is just going to be 0. So it's the same thing like with entropy. If you have a diatom like O2 or H2, then those Gibbs free energies are going to be 0. The only time it does not have a 0 number is when we're dealing with the entropy. Because it is a gas, it's going to have a positive entropy value. Now that we have all of these values, let's plug it into the reaction equation and solve for our Gibbs free energy for the overall reaction. So now we just have to write out the overall equation. I know it looks a lot more complicated than what it really is. So we're just have to do the sum of our products minus the sum of our reactants. That would just look like delta G equals, I'm going to put big brackets and I'm going to put all of my products here. And don't forget your coefficient out front. Well, we'll just go out front of the delta G value. So now I just need to plug in those numbers that we got from the table in the back of the book. And that gives us 3. Don't forget to include the moles because they're going to cancel out. Negative 394.4. Negative 237.1. And that's going to be your sum of your products minus your sum of your reactants. I forgot to write it all out, but don't forget your mole out front. So if you plug all of that in, I get a delta G value for this reaction equal to negative 2108.2 kilojoules. So free energy and entropy are also relevant to the formation of solutions. An example of this is when you dissolve ammonium nitrate in water, it's going to be highly endothermic and is used as instant cold packs. So having it absorb heat makes the surroundings of it instantly cold, and that's why it's a good example of this. So a positive entropy of solution indicates that the total energy needed to separate the particles is greater than the energy released by solvation. And then why would this process occur spontaneously? Well, the particles in the solid ionic compounds are highly ordered, but in solution, these particles become dispersed. So remember when we discussed like in NaCl by itself, it's Ionic, it's very, very ordered. It has a very, very high melting point, but the second you put it in water, it instantly dissociates to become sodium plus and chloride minus in solution. So then it becomes dispersed, having a higher entropy. So this increase in entropy is sufficient to overcome the positive enthalpy change associated with the dissolution of many solutes.